Hi there guys, my name is Charles Msipa. Welcome to another presentation, a kind of tutorial based on the assignment which you had recently. In this tutorial, I would like to discuss some kind of central ideas on presenting solutions and tie together some ideas around these exercises. So let's start this way. The first exercise said, use the first principles to determine f prime of x. I hope you are all used to this notation, which is f prime of x, which actually denotes the derivative of the function f of f with respect to x. Or we can also, if we take f of x as y is equal to x, we can also say dy dx. I hope you are used to these different notations. Right. So when we talk of the first principle, sometimes people will talk of the first principle, and they will also talk of the using the definition. You remember the derivative of a function y is equal to f of x is defined in terms of the incremental quotient. In this case, let's use f prime x equals to the limit as h tends to 0 of f of x plus h minus f of x all over h. In this case, h denotes what we normally call the change in x. Now, if we've got 2 points where we're evaluating f, like in this case, f at x, and we add a change in x, then we evaluated f at x plus change in x. Then the limit of this incremental quotient, if it exists, then that's what we call the derivative of the function there. So please note that when we talk of first principle or the definition, you are required to do it via this calculating this limit, because later, remember, we develop rules like the power rule. For example, if we've got y is equal to the power n, we derive that if we want to calculate the derivative, this will simply be dy dx equals to n multiplied by x to the power n minus 1. So when we're using this kind of what I can call mechanics of the differentiation, we'll say here where we were using what we call the power rule. And when you get to other functions also, we have similar different types of rules, or sometimes we've got immediate derivative, like for example the derivative of a function y is equals to cosine x. The derivative of that will be y prime equals to minus sine of x, which also can be derived via the definition this way. But once we've learned it, we just need to have to learn the derivatives just like we learn the alphabet. The only thing we have to know is to master rules like power rule, chain rule, and so on in differentiation. So now, coming to these exercises, let's start with the first one. My purpose of discussing this is to, I know you get the memorandums, but the problem is sometimes the solutions in the memorandums are very summarized just to help the lecturer mark your assignments, but there are some things in between which you are not really explicitly revealed in the memorandum. So let's start with our first exercise here, which is f of x is equal to x squared. So we start by denoting and say f prime of x is equal to the limit as h is approaching 0 of this incremental quotient, which is f at x plus h minus f at x over h. So you must remember that when we're calculating limit like this, we're saying h tends to 0, but it must always be, we mustn't never lose sight of the fact that h is not equals to 0. Now, so what we've got to do here, we know that our function is y is equals to x squared. So we need to evaluate at this point. In this case, what we do, we're doing it on the side here so that we don't get this a bit crowded. So what we have here now, we have x plus h. In other words, we are evaluating the function x squared at x plus h. And then this is a binomial which we normally expand as x squared plus 2xh plus h squared. So now, which means we need to put this in the numerator by substituting there. Then we have got here limit as h is approaching 0 of this expression x squared plus 2x by h minus h minus f of x, which is the original expression of the function, which is x squared, all over h. Now, at this stage, you can see that this term x squared and that one, they make 0, so we get rid of them. In the next line here, we're going to have limit as h approaches 0 of 2x h plus h squared. So this is supposed to be plus h squared, like it is there, divided by h. Now, I hope you know that normally if we've got a function, for example, a polynomial like f of x equals to 2x squared plus x, and we want to calculate the limit as x approaches let's say 1, because this is a nice function, it's defined everywhere. What we normally do is we do direct evaluation here, like we saw in the previous assignment. Then we'll just say 2 times 1 squared plus 1, and then get this limit as equals to 3. So when we get to this situation, our first temptation actually is to calculate the limit via direct integration. But if you do that here, you will see that you will obtain actually an indeterminate form of this. Just looking at this exercise and reflecting a bit on direct evaluation to compute a limit, you see that you land at an indeterminate form of this. So once you see that kind of situation, your way of avoiding this most of the times will to factorize, to see if you can factorize the expression which you have. Like for example, in this case here, we can take out the common factor h and write this as follows. Say limit as h is approaching 0, common factor h there, then we get 2x. So this is h squared, 2x plus h all over h. Now when we've factorized like this, I hope you can see, remember we've factorized the h is not equal to 0, so this is h over h, that will give us a 1. Then you end up calculating the limit as h is approaching 0, limit of 2x plus h. So when we landed this one, we sort of get a kind of a polynomial which depends on h, which is defined everywhere. Then we resort to what? To evaluating the limit directly, because remember, if the function is continuous and is defined, the limit is coincide with the value of the function. So in this case, this will be 2x plus 0, which will give us 2x. So what I want to actually reiterate on is this point here, that whenever you see this kind of a situation, please try to see if you can find some factorization which will actually make you bypass this obstacle of getting an indeterminate form, then compute a limit and arrive at that. So that would be in this case, this would be the derivative of f of x, where f of x was given as y is equal to x squared. I think That's enough for that. Then coming to the second exercise, as you can see, it's very similar. I hope this explanation suffices, and you can be able to do this one easily, taking into account the points you have highlighted. So let's maybe now pass to the exercise number 2. So now when we get to number 2, it says use the appropriate technique of determining f prime. What are the techniques or the rules which we have so far? You reflecting on that, number 1, I think we've got the power rule, and number 2, the chain rule, and number 3, we also got the product rule stroke quotient rule. I'll just take the product and quotient together because of the relationship between the two of them. Okay, in this case, I'm just trying to say when you're multiplying and or dividing, it's almost one and the same operation, but though the quotient rule for differentiation is quite something different. So I'll just write that to just summarize a bit. Okay, so now you must notice the difference here. When you are using the techniques or rules, whatever you want to call them, you don't need to always go back to the first principle or the definition. In other words, you don't need to go to this limit of the incremental quotient as limit as h is going to 0. In other words, once we've learned that we have derived some standard derivatives using the incremental quotient, we don't need always to go there. We can use these rules and then compute our derivatives f prime of x. So what we're going to do now, we see that the first function here we've got is f is a product of two polynomials, x cubed minus 2x squared plus 5 multiplied by x to the power 4 minus 3x squared plus 2. So there's no need to remove brackets here in order to do this. I think you get yourself into some kind of tedious work unnecessarily. So what we can do now, take number 2.1. Please, when you're writing this solution, like in your compiling the solutions in your assignment, you really need to write this question. You don't need to really maybe to announce what you're supposed to do there, but you can write 2 and then 2.1. The first thing to do, you must copy the exercise of which is given in 2.1, which in this case is f of x equals to x cubed minus 2x squared plus 5 multiplied by x to the power 4 minus 3x squared plus 2. Then the next thing, you may write maybe solution if you want. If you don't want to write solution, but it must be clear where you start differentiating. In this case now, we would say now df dx. I'm just trying to use another notation here, df dx. In this case, we have to recall our product rules. Let's say we've got u multiplied by v, and you want to compute the derivative of that. They want to go this way. Say u times v prime is equals to u prime times v plus u multiplied by v prime. That's what the product rule states. So we can simply declare our u, in this case in the same order, to be this function, and our v to be that. So what will happen now, we'll come here, apply the power rule in each of these terms. In this case here, this will be 3x 3 minus 1. I'm drawing this explicitly so that people can see what is happening, for those who are still like not sure of exactly what is supposed to be done here. Come to the next term, this is minus 2. Then in brackets here, small brackets for this one, that will be 2x 2 minus 1. I want you to clear that there are two 2's here. This 2 which was given as a coefficient there, minus 2. And then this one is the one for the power rule. Then plus, in this case, derivative of constant, by now we know is 0. Then we multiply that by that function without differentiating, like we can see here. That will be x to the power 4 minus 3x squared plus 2. Then plus, we copy the first function u as it is without any differentiation, then which is x cubed minus 2x squared plus 5 multiplied by 4x to the power 4 minus 1 minus 3 brackets 2x to the power 2 minus 1. So at that stage, I've shown explicitly what I'm going to do, what kind of computations in terms of differentiation I'm going to do. The next thing will be simple to simplify this and write it more nicely and compactly. In this case here, we just simplify these calculations here. This will be 3x squared, and now we are going to have a 2 times 2, which is going to be minus 4x multiplied by x to the power of 4 minus 3x squared plus 2, plus this function here is x cubed minus 2x squared plus 5 multiplied by here 4x cubed minus 6x. Right. In terms of our differentiation work done, I don't think it's really necessary to remove brackets here. Then you have got you can remove them, but if you've got time in abundance, but if you don't need to, you can just leave this. You've fully demonstrated that you know what you're supposed to do in this exercise. Right. Turning to 2.2, I think you can see that if you reflect nicely, you will see that you combine chain rule and the quotient rule, depending on how you handle this function. So let's take this function as it is. Let's say 2.2, the function given is f of x equals to x minus 1 over x to the power of 4 all to the power half. I hope you can see that in this case here, there are many functions involved here, and we have composition of functions. That's why we need chain rule. So first of all, we've got the quotient of these two, but the quotient of these two is an argument of the power function, in this case power half. So writing now, our solution will be as follows. If we now say here f of x prime, if we apply the power rule, what we need to reflect on is that in this case we've got a situation which is more or less like this. We've got y, which is f of x to the power n. So you've seen before that if you've got such a situation, what we do, we'll say dy dx, then you apply the power rule to the n here as a power, then say n multiplied by f of x to the power n minus 1 multiplied by f prime. In other words, when we look at this function, we must see that the leading function is, now the main function here is the power function, and this f of x here becomes the argument of this power function. So what we see here, so this is supposed to be f prime. So what we see here stated here is that whenever we're differentiating a function, we focus mainly on the main function, now the leading function, in this case the power function. Then we differentiate it according to the technique or rule which we apply to it. Then we multiply by the derivative of the argument. So we continue this until we get to the simplest argument, in this case, which might be x, and in this case the argument x will be just differentiated as x dx dx, which will be 1, which normally we don't write this because multiplying by 1 is a neutral multiplication, we just leave it. But we must understand that as we differentiate following all the appropriate rules until we get to the simplest argument, which differentiates to 1. So when we come here, we're going to do exactly this and say half there, retain our argument like we saw here, we retained our argument there. In other words, we keep the same argument divided by x to the power 4, then to the power half minus 1, like we have there. Then after that, we have to multiply this by the derivative with respect to x of the argument. In this case, the argument is 1. So it's x minus 1 over x to the power 4. Now I'm talking of the argument of the power function which is there. That's how it goes. So then when you are at this point now, we see that the function we're given there is a quotient. So we must be careful there. Then this will be equals to half x minus 1 over x to the power 4 all to the power minus half multiplied by, then we can apply our quotient rule here. And remember, if we've got, let's say, u over v, and we need a derivative, recapping on quotient rule, this will be u prime multiplied by v without differentiating minus u multiplied by the derivative of v all over v squared. So that's what we're going to apply here. So if we square the denominator here, we're going to get x to the power 8 using rules of exponents. So differentiating the numerator, we'll get 1 multiplied by x to the power 4 minus x minus 1 in brackets multiplied by 4x to the power 3. I'm not going to be faster on that one because I think everybody is now familiar with that. Then simplifying this, then we get here x to the power 4. Maybe we can remove the brackets here because it's a simple expression. Then we got minus 4x to the power, this is x to the power 3, there is x to the power 1. So we're going to have here 4x to the power 4 plus, because of this minus sign here, plus 4x to the power 3 all over x to the power 8. And this is multiplying this. Now what we have here is power minus 1. So what you can do, we know that minus 1 there will mean we must get this inverted. Then we write it this way: half square root of x to the power 4 divided by x minus 1. Now we can now continue this and simplify this as follows. We can calculate the equivalent of the numerator and that of denominator. Then we end up with x to the power 2 divided by 2 square root of x minus 1 multiplied by, simplifying here, we've got minus 3x to the power 4 minus 3x to the power 4 plus 4x cubed all over x to the power 8. Then we can now simplify this term and that. Then we're going to have the following. Simplifying that, we subtract 2 from that, we're going to have x to the power 6 here. Then we've got here 1 over 2 square root of x minus 1. And again, in the numerator here, we've got a common factor, which is x to the power 3. Then multiplied by x to the power 3 brackets 4 minus 3x all over x to the power 6. Remember, we got 6 after when you simplify that. Then simplifying again, then we've got this simplifying to 4 minus 3x all over. Simplifying, you're going to be left with x cubed here all over 2x cubed by the square root of x minus 1. So I think you can see now that this exercise was really sort of packed with and we had the power rule and the quotient rule together in the same exercises, which actually gives you a message that these rules of differentiation, power rule, product rule, as we know them, we normally find them in one exercise when we need to apply them appropriately. So it's not a question that we're going to use this rule for this exercise and that exercise. We can find in one exercise all the relevant and different rules which we have learned. So I hope you have got that. So this is, I think, the end of exercise number 2. Then going to exercise number 3, we have the following. Now we've got a situation here which involves the Lean functions, which in this case we must know how to deal with Lean functions, its properties, and so on. Now for this 3.1, we'll write that and write the expression which is given. We always have to write this expression which is given so that when we start the solution, even the marker can make a reference from what you're starting from, rather than writing solutions in some kind of strange way. So in this case, we're going to have a Lean of 2, also not x but t. This is the other thing. Please don't change the variables which are given in the exercise, because some people sometimes you give a function in terms of x, then you write in terms of t, given in terms of t, you write in terms of x. You must write the exercise exactly as it was given by the examiner or your lecturer. So now we have got Lean t to the power t. Now moving on to solving this problem, we need to calculate dy dx. By now, when we do this exercise, before we do that, you must now be very, very familiar with that. If you've got a function Lean of f of x, the derivative of this always comes out as y prime equals to f prime over f prime. Now for the case of finding a way of remembering this, like a trick for memorizing, of course memorizing with understanding, you must unpack this way and see that this is 1 over f of x, and notice that f of x here is the argument of the Lean function there. Then if we take it like that, this will be multiplied by the derivative, in this case, of the argument. So we can simply say the derivative of a Lean function is always 1 over its argument multiplied by the derivative of the argument. I think it's nice to say it like that. It is easy to remember. So when we get to this, applying exactly this, we'll say 1 over the argument, in this case 2. Oh, sorry, look, I've done the same mistake which I was saying you shouldn't do. This x again is coming up here. I think after writing a number of functions using x, someone gets into a habit that you are differentiating in terms of x, but you must be very, very careful. You must just not write loosely and write anything there. So dy dt. So in this case, it's 1 over the argument, which is 2t plus 3, multiplied by the derivative of the argument. In this case, I'm writing in this way so that if you write it this way also in your notes or whatever, then when you are studying, you can remember exactly the full process. So the first line I'll write is exactly the same. 1 over the argument multiplied by derivative. Then you see what I'm differentiating here. 2t plus 3. Plus, then when you come to this kind of situation, before you can differentiate, you need to simplify by applying the properties of Lean. In this case, Lean t to the power t will be the same as t Lean t. Then immediately what we've got there, we've got a product of one function t, y is equal to t, and the function y is equal to Lean of t. Then you apply our product rule. In this case, it will be 1 for the derivative of t with respect to t. So maybe let me write it that way so that this is explicit. So in this case here, we'll be differentiating t with respect to t and multiplied by Lean t plus, in other words, applying the product rule now, plus t multiplied by the derivative of ln t with respect to t. So in the next line now, we can now simplify this as differentiating here. We get 2 plus 0, then we get here 2 over 2 t plus 3. Now coming here, this is dt over dt is 1, so we remain there with ln t, and then plus t. Then following exactly the same rule we had here, it will be 1 over t, which will be the argument of that, multiplied by dt, which is 1, like we've seen here. Then we'll remain here with 1. So we're going to remain with something like t multiplied by 1 over t, which is 1 over the argument of ln, multiplied by dt, which is 1. I'm just writing it here explicitly just to put across this message I'm saying here, that you must look at it as 1 over the argument multiplied by the derivative argument. But normally, because this is equal to 1, we normally don't write it, and sometimes we don't even emphasize it when we are talking about these things, assuming that it's understood. But I just feel that sometimes we need to talk about it very, very explicitly. So then, simplifying this now, we know we're going to get here 1, and then writing our final answer, it will look as follows: to be dy dt equals to 2 over 2t plus 3 plus ln of t plus t here plus 1, since it's t multiplied by 1 over t. Then we've got our exercise done there. So guys, if this, I know this is a video presentation, you cannot stop me and ask, but if there's something you don't understand, you can always rewind your video. But if you still don't understand, please post your questions on our discussion forum. Then I'll maybe make another presentation which is sort of explaining your questions the way you ask them. Okay, getting to number 3.2, in this case, we've got a g of t, which is 2 to ln of 2t multiplied by ln of e to the power 2t. Right, so we have here 3.2, which is g of t, which is equal to 2 ln of 2t plus ln of e to the power. Okay, given this exercise as it is, first of all, I think we need to simplify this and write it simpler as follows. This will be 2 ln 2t plus 2t ln e. Remember, ln e is same as log base e of e, which is equals to 1. And the other that's one argument you can use here. The other fact is, remember, if you've got function y equals to ln t, then the inverse, which you can denote this way, y, there is e to the power t. And remember, if you have function f composed with its inverse in any order, like for example, inverse applied to f, what you get here is the identity function now to get back the argument. So we could apply either this, that, to get to the following, which is 2 ln 2t plus 2t. Now once we have simplified like this, now that's when we can start differentiating this function. In this case here, we'll say dg dt, derivative of g equal to t, Now we've got to know the derivative of the exponential functions. I hope you recall that if you've got a function y is equal to a, and function a, the derivative of this will be y prime, which will be the exponential function itself. I hope you have noted that exponential functions, when you differentiate, they always bounce back exactly as they are. In this case, multiplied by the ln of the base and multiplied by the derivative of argument. In this case, I'm going to write it as dx. In ours here, I'm just accommodating the fact that even if this argument was any other function like sine or cos, then the derivative would simply be y prime equals to a to the power cos, whatever argument cos has got, multiplied by ln of the base, multiplied by the derivative of cos with respect to x. So if you know this, you just need to adapt it here. In this case, you are dealing with a function of t. So what would happen here is an exponential function. It will be simple. The exponential function bouncing back in the derivative exactly as it is, multiplied by the ln of the base, in this case ln of 2, then multiplied by the derivative of the argument. In this case, I'm talking about the argument of the function, the exponential function base 2. Its argument is ln of 2. So with respect to t, which will be now ln of 2t. If you look at what I've written here, is exactly what I've sort of pointed out there. So then, differentiating slowly, we've got here 2 ln 2t. Already that's the derivative of exponential function, multiplied by ln of 2, which is ln of the base. Then differentiating here, we'll say multiplied by 1 over the argument, in this case, which is 2t, multiplied by the derivative argument. In this case, we're differentiating 2t. Remember, this is simple, a linear function 2t. The derivative of that will be simply 2. So we multiply here by 2. Then the next thing is to just write this thing in a more compact way, a simplified, which will end up as follows. That will be equals to 2 to the power ln 2t multiplied by ln 2. Simplifying here, we can see that that will give us 1, then that will multiply by 1 over t. Now finally, we can write this as, this is a number coefficient, we can write it as here ln 2, put it in brackets there to avoid ambiguity. Then we write the 2 ln 2t all over t. That will be the derivative in its simplest form. I hope this discussion is enriching the memo you've got. Then you can understand what is not written in between the lines of the memo given to you. Otherwise, at this point, I would like to say thank you for listening. Please keep on giving me feedback via my email given below.